Mm-hmm.
Okay, so we're delighted to have Grisha Falkovich to tell us about his work with Vladimir Rosenhaus on wave kinetics. So Grisha, tell us about the latest, most postmodern developments.
Yeah, postmodern, because if postmodern means that there were at least two stages before, and there was a classical stage of Boltzmann where people derived kinetic equation, and then there were modern, what is called, I guess by Uhlenbeck probably was called the modern kinetics, which more or less 60s, 70s, and 80s, where people started computing corrections to kinetics, to classical kinetic equation, and discovered a very important difference between equilibrium and non-equilibrium. And in a sense, what we're doing with Vladimir, we're doing kind of a next stage in kinetics is postmodern kinetics, in a sense that we are doing corrections to the kinetic equation for waves, not for particles. And we are using states which are very far from equilibrium, not just transport states where you impose a gradient. A little bit later, I'll be more specific. I'll just show you this divergence in Boltzmann equation. But for now, my problem is as follows. Here is on the left, you see the picture of a sea when wind is not very strong. And you see that there is definitely a very far from equilibrium state. There are many, many waves with very different wave lengths running in different directions. And but the steepness of these waves is relatively small. So if you look there, you don't see much very steep waves which tend to break and create a foam. You don't see much white caps. And apparently the parameter of nonlinearity for this wave, dimensionless parameter of nonlinearity, is just an angle of water surface. And it's clear that on general it's small, and typically what is shown on the left is something like 10 to minus 2. Maybe a little bit like 5 to 10 to minus 2, but that's a typical mean angle of inclination. Now, if you look at the right, you'll see waves running at much stronger wind. It's already, I mean, real oceanic turbulence, and you see a lot of foam, which means that you see a lot of waves whose angles are 30, 40, 50 degrees, and wave break, in particular, Stokes wave has a cusp which is 120 degrees at the top, so it's definitely something which is a very nonlinear system. So both these states are very far from equilibrium, but one corresponds to what's so-called weak turbulence, namely that we do have a small parameter of nonlinearity, and the right side is strong. So in a sense, what we will try to do here, and I believe that this work is just the beginning of a long stage of development, as we'll try to go from left to right, more or less the way that theoreticians know how to do it, by summing diagrams. Namely, we look at the left, we say that we have a very, very weakly nonlinear system, even though far from equilibrium. We'll derive after Peierls, Hasselmann, and these equations. And then after Zakharov, we'll write an exact solution to this equation, which will describe a turbulent state of weak turbulence. Incidentally, Hasselmann got a Nobel Prize for applying these kinetic equations to real seas, and Zakharov got his Dirac medal for solving this equation. And then we'll try to see what are the corrections to kinetic equation. Just next correction on linearity, and we discover the surprises that people discovered back in modern kinetics and more. We discover more surprises because we are much farther from thermal equilibrium. So that's more or less the setting. Let's go. This is a formal abstract. I'll probably skip it. I just go directly into the Hamiltonian. When I was a student, they used to say, I mean, stop talking, write Hamiltonian. So here is a Hamiltonian. We consider Hamiltonian, which has a quadratic part which describes propagation of wave with a linear frequency omega. And then it describes a scattering of 4 waves. And here the magnitude of the scattering is lambda. And we'll consider limit of lambda going to 0. That will be a formal limit. Everywhere will be accounting for the lowest interesting terms in lambda. Generally, it's maybe the very beginning, it's worth saying the difference between renormalization of what we mean and what people in field theory mean. So for us, omega and lambda are totally true expressions. They are derived from the equation of motion, which are valid for all turbulent state and below what is the ultraviolet dissipation scale. Their frequency of a wave propagating in a quiet sea, no other wave present, and interaction of 4 waves in a quiet sea. Now, our sea contains a lot of other waves, and we want to compute what would be the change to the, let's say, frequency, or what will be the change to lambda. We'll be mostly focusing on lambda. When we have a quartet of waves interacting in a stormy sea, when there are many other waves around. So a kinetic equation is obtained in a relatively straightforward way. So let me remind you how it's done. You write the equation of motion, which is dAk over dt, is just a variation of Hamiltonian with respect to AK complex conjugated. This would give you a linear term. This would give you a cubic term. Then you multiply it by a complex conjugated, and you get equation into the pair correlation function, or it's called occupation numbers. So generally, this equation, of course, has a closure problem. So time derivative of a second moment is expressed in this case through the force moment. Quadratic term cancel out because it's a real part. Now, what we assume that because there are weakly interacting waves and there are many random factors in the sea or whenever which chaotize their phases, we assume, not that we can prove it, and mathematicians will probably try to prove some things about it not in the nearest future. They're still working near equilibrium. We assume that the statistic is close to Gaussian. So in a sense, we'll be computing corrections to this Gaussian statistics. Is the zeros Gaussian approximation, the imaginary part, the force part, cumulant is of course 0. So we would like to compute the first non-vanishing order contribution, which is already non-Gaussian correction because it's imaginary part, it's a cumulant. And then next corrections. So a technical tool to do it is to, since time immemorial, but I don't think it's completely harmless, even though everybody does it, we also do it, but maybe at some point we'll need to see if there could be difference between different way of imposing stochasticity. We impose stochasticity as follows. We add to our equations a Gaussian random force acting on any mode independently. So the pair correlation function of this force is the delta function of k minus q. It's also white in time, and it has some power spectrum. And we also add dissipation. Now, and then we assume that the ratio between f and gamma is some prescribed function nk, such that it would guarantee us the stationary state of this equation. We'll be studying only steady state, only steady cascade turbulence, but we consider this going to 0, like infinitesimal but balanced random kicks and dissipation. In equilibrium, it's totally legitimate because this is just if you substitute nk equipartition. But surprisingly, that the equation obtained in this form also have a turbulence. Maybe not surprisingly, but just to say that it's far from evident that the equation obtained in this way of introducing chaoticity have a very far equilibrium solution. That's what Zakharov found. Okay. Then technically you just do standard perturbation theory, namely you write your dynamical equation in the k omega representation. So you have A, your amplitude is F, then A cube, this is still exact relation. And then in this nonlinear term, you start substituting series. First you get a cubic term, then you get quintic term, etc. And then whenever correlation function you want to compute, you just multiply series for A. If you want to compute for force moment, you just multiply for infinite series and sort the terms. I know that my field theoretical friends, they find it very much 20th century, but technically that's what I always do, at least up to the second order when I'm checking the computations. So now in the zeros order, when we in this form, at the right, let me remind you, is of this time derivative is the force moment, and if I substitute in 3 a's the linear expression and in 1 cubic, then I would get this expression, which would be technically cubic in n's. Okay, and because there are 4 different positions where I can substitute cubic term, then I get this equation. It is actually first, I guess, it derived Well, in some form, it's Born-Oppenheimer, but it's a PhD of Pyros 1921, so it's 100 years old. It's a very close analog of Boltzmann equation. You can write quantum kinetic equation of which this is the classical limit and Boltzmann equation is a quantum limit. So in a sense, they are kind of two limits of the same equation. Okay. Now, this equation describes the evolution of occupation number because of scattering. It has two integrals of motion. First, its energy, and then its total number of waves. We'll be interested in turbulent cascades, and we'll be interested here only in the direct turbulent cascade. It's a beginning of a long program, so I'm not going to cover everything. I just want to take one case and see how surprising are the results. So you can write this equation in principle by multiplying it by omega k and k to the d as a continuity equation for the energy density. This is your energy spectral density in Fourier space. And so if you want a stationary solution, then you can either take P equal to 0, that would be equilibrium, and it would correspond to equipartition, or you take P constant, and that would be a cascade. So now if you say that you want P to be constant, non-zero constant, then you can just get your occupation number by power counting, assuming all integral converge. So you say that your P, I mean, it's just this right-hand side multiplied by omega and integrated once over kd. So it would have 3 n's. It would have k in the power 2 beta, which is the scaling of lambda. And it would have 3d because there are integration over 4 different wave numbers and 1 delta function of wave numbers. After power counting, you just get this is a Zakharov solution, which Zakharov got in his PhD in 1967, and this is a solution. Now you may plug it into this, which incidentally Zakharov did by hands, and he get, in the simplest case he was solving, he get 18 beta function, was quite a non-trivial exercises, and they get all them cancelled. But generally, you alternatively may just check that the integral converge. If the integral converge, then your power counting is legitimate and give you a solution. So now you can ask how actually your weak turbulence remains weak or getting strong as you change the wave number. So it means that you need to define some dimensionless parameter which describes a ratio of a second term in the Hamiltonian to the first one, which is essentially you can roughly estimate as this bare vertex of interaction times wave number. This is just the total number of waves divided by frequency. Okay, and if you now plug here nk Zakharov solution with a gamma given by this, you get this scaling. This tells you that beta is a scaling of your lambda and alpha is a scaling of your omega. So it tells you that beta 3 over alpha, this is something which determines whether your turbulence is getting strong or weak as you go along the cascade. K naught is your pumping scale. This is a large parameter as you go away along the cascade. So if your lambda grows faster than omega, I mean divided by 3, then you're getting strong, and at some point your weak turbulence approximation is getting close. If it's not, then it's getting better. And this is what written in the books that we wrote with Zakharov and Vog. It's kind of like everyone believed until this our work. So now, really, to get the validity, of course, we need to compute corrections, real corrections, and substitute the Zakharov spectrum and see what is the real power by which this correction depends on K. The basic, I mean, you probably know there is this old book which we wrote with Zakharov, which contains this incorrect statement, but many other correct statements too. It's now reissued. There is a new printing of this book, and we're already signing the publishing agreement on the second edition. So it will be probably next year a second edition. And also there is a shorter version of all this. We gave with John Cardy and Christoph Gavetsky, we gave 3 courses and organized it in a book. So kind of shorter version on this weak turbulence you can find also in this book. Okay, so now we need to study convergence. And to study convergence, we really need to define what are the asymptotics of the vertex when there are 2 wave numbers much less than other two, or there is one wave number is much less than other three. So there is some scaling exponents beta 1, beta 2, and beta 3, which defined it, and which good people of 70s, myself included, computed and get their PhDs computing this beta 1, beta 2, beta 3 in different cases. And you get a criterion. Here is на самом деле something surprising, which I found in my PhD, is the following thing, that naively you would expect that if you take this right-hand side, it's an integral over 1, 2, 3, or in this case 1, 2, 3, 4, but 1 is equal to k. So it's equal integral over 2, 3, 4. And if you plug power solutions, your lambda is scale invariant, your n is a power law, your omega is a power law. So you would get divergence either at one end or at another. And yet the structure of kinetic equation is such that it contains two constellations at infrared and one constellation at UV. And that provides for a window of locality. And what I found long ago in my PhD is that Zakharov solution, at least for three-wave interaction, is usually right at the center of this window of locality. In a sense, it balances contributions between interaction with long wave and short waves. This is what we call with Zakharov a counterbalanced locality of interaction. And in a sense, this is the way that Zakharov found his first solution. He just tried middle and it worked. And then he understood about flux. He did not know about flux or any fancy notion. He just looked at the divergences, saw that there is a locality window and tried middle. And later we understood that this middle is where it must be. Okay, so now we will consider cases where this locality is satisfied, namely all the integrals in kinetic equation, what we now call bare kinetic equation, are convergent. So the Zakharov solution is the solution of this equation. Okay, and here our present work starts. So now we compute a next order correction to this equation, which is pretty straightforward. Actually, Polyakov did it at the early 90s. It's pretty strange that Zakharov and Polyakov did, and they were kind of close friends, and you know, they were hiking together. So why they did not sit together 40 years ago and compute this thing is not clear. But Polyakov actually at 90s computed this first order correction, and I also did it when I was PhD student, and we all knew that they are divergent generally, and we kind of did not think much about it, even though Polyakov probably thought much about it, but he had many other things to do. So let's look now at this correction. You see that they have extra factor over here, and they have extra lambda over here. They are next order in lambda. They all have this factor which guarantees that equilibrium is a solution. So equilibrium will be solution. And then you look at and you ask the same question, whether the integral is convergent or divergent, and you find out that there are some could be convergence at infrared, but there are always convergence at UV. When P2, P4, and P6, let's say, go to infinity, then you have your locality window shrinks to 0. It just disappears. This is how this integral actually look like of this correction. And then you find out that if your beta 1, remember, is a scaling exponent, this beta 1 is this guy, is how your lambda scales with your large wave number. So if your large wave number scale is a power of beta 1, which are now fortunately known for all cases of turbulence, and for alpha, which is a scaling of omega, if alpha is less than 1, then for any beta 1, you have a UV divergence. In particular, you immediately see here that for surface water waves, where omega is square root of k, where alpha is 1/2, you always have UV divergence, guaranteed. Just asymptotics of lambda, which is pretty well known, guarantees this. In cases like spin waves, which are also addressed, or plasma waves where alpha is 2, it could be cases where actually converging. In the trivial case where all betas are 0, which is a Gross-Pitayevsky equation or nonlinear Schrodinger equation, where just your lambda is a constant and your alpha is 2, you are converging. So your Dirac cascade is really don't have any UV problems. So your compute corrections, they're all finite when your K maximum goes to infinity. But there are many other cases, in particular spin waves, where this divergence is also present. Okay, so now you need to go to next orders and see what are the most diverging term in the arbitrary order, which is by now kind of a standard thing in field theory. And when you actually look back in the old classical works in this modern kinetics, you recognize that what this guy called ring diagrams, and then what other guys calls sausage diagrams for electrons. I mean, Vladimir can tell you a long lecture, because people like everywhere, at large N expansion and field theory, people everywhere more or less see the most divergent terms presented by such diagrams. Not necessarily UV. For example, in kinetics, the divergences are infrared. I'll tell a little bit more about it later. So you find out that even though at high orders there are many different topologies of diagrams, this linear chain of bubbles is your most divergent diagram at every order. And this is beautiful, which immediately shows you what happens when you add one more loop. It's essentially you kind of replacing your lambda in the this last lambda in the previous group by some kind of this integral, which adds j plus 1, extra bubble, extra integration, but they all are of the same very similar nature. And then you can derive what is called Schwinger-Dyson equation, which is essentially integral equation, which relates your non-renormalized force moment to the renormalized force moment. I'm now jumping over a lot of technicalities, which means that, of course, this perturbation theory is done in k omega space. Like, remember when I wrote the naive expression of dynamical equation in frequency wave number representation. And then you need to integrate it over omega if you really want to get kinetic equation, which is written only in k space. It's written for single time moments. So this could be found in a pretty long appendix to our work, but at least in some cases we were able to do it to the leading order in lambda. We find an integral equation on the renormalization of the vertex now in only wave number space. This is by itself already kind of remarkable, because generally nobody guarantees you that you would get an expression. But in this particular case, this is a leading order. It's in a sense kind of lambda cube expression. We don't venture beyond lambda cube. We just sort all diagrams corresponding to the most divergent diagram of lambda cube. They are of all orders in lambda, but they are all of the same nature of these bubbles. And this is this integral equation, which is pretty familiar in many field theoretical contexts. Now we need to solve it. It's an integral equation. And it's fascinating. I mean, we're now starting to try to solve it for real, for oceanic waves, where lambda is unbelievably complicated functions. It changes sign many times. It has quasi-singularities. It will be very interesting thing. But for now, what we did with Vladimir, we solved it in a very in two simple cases. And we already discovered a lot of very interesting and unexpected results. So what are the trivial cases in which we were able to solve it? They're actually physical. I mean, there are physical systems like this. So first case is when we have a product factorized lambda. And second case when we have a sum. This is exactly a spin wave by exchanging interaction. In this case, we can just, this is an exact solution of this integral equation, which is expressed through these lambdas. And in this case, through these lambdas, and in this case, through this lambda. And R is just what we call loop integral. When you look at here, you see that it is this L1, which, like in field theory, it's essentially summing of geometric series. So how we get this expression? We get a geometric series summing all these bubbles, each one in this particular case of this product just give you the same factor, which is L1, and so you sum geometric series, you get this expression, which tells you that your L1 in this case is your effective nonlinearity. It's a dimensionless parameter. It's an integral. Technically, it has the same dimensionality as our naive estimate, which was lambda n divided by omega. But now it's an integral, namely that we must really integrate and see where it leads us. And in particularly, if you plug this vertex in kinetic equation, that we get what is a renormalized kinetic equation. Very similar to what Oppenheim and Kawasaki did for Boltzmann. We find the denominator over here, which renormalizes effective lambda. Okay? And again, we must take it, consider it to be spectral density of waves multiplied by omega, requires that the flux is constant. Now we need to solve this equation, which we did not yet. But it's a fascinating thing now to have a new equation to solve. But at least we may now try to analyze it, how actually we expect it to behave. First of all, we can show that this renormalization of T guarantees you that there are no UV divergences in this new expression. Except there is kind of hypothetical cases which technically could exist, but I don't know of any physical system where it exists, that it's really, there is a remaining UV divergence in the L1 itself. Maybe there are some fundamental reason why there is not, or maybe there is some exotic system which L1 can still have UV divergence, but the integration over P2, P4, it's UV conversion. But what we discovered, to the great surprise of us, at least of me, is that it always has infrared divergence. So L1 as an integral, really, if you look at it, it scales as your K0, which is a pumping scale for direct cascade, in this power. And if you plug here the Harov solution, you find here minus beta over 6. And because for our waves, beta is always positive, by the way, opposite to particles. So our interaction increases with wave numbers. That we usually have some kind of a Goldstone-Adler theorems, which means that interaction and omega go to 0 when k goes to 0, and they increase when k increases, because we are working essentially with some kind of a continuous limit series. So because our beta is positive, then we have infrared divergence, guaranteed, which means that our effective coupling is different by scaling, by a large parameter from a naive coupling. So if now you say that my correction to the Zakharov equation behaves like this, actually you'll find out that the imaginary part of Alice is complex integral. Imaginary part does not have a divergency because it contains delta function of omegas, and real part has a Cauchy value integral in omega, so it has a divergence, and it is your naive bare coupling, which you start from, multiply by this large number, which depends on k always. Okay, so even though your ek could decrease with k if beta is less than 3 alpha, this adds to it something. So you may find out in a situation where your naive dimensional power counting shows you that you're actually getting into Vika and Vika turbulence, and your real account for it tells you that you're actually getting into strong turbulence. So what's going on? What's the physics behind it?
So quick question, Grisha. So if I understood correctly, so you're assuming, you know, as you say, perturbation theory and weakly Gaussian, but doesn't this, what you just told us, mean that the corrections are large and so that it's not self-consistent?
Of course, all this is not true when these corrections are large. They all still work when this delta n over n is small. What we are telling is they are small, but they grow faster than we expected, which means that they are getting afford a unity, which is still describable by this equation, when they are getting afford a unity much earlier than you would expect. For example, for C waves, by my estimate, it shrinks 10 times the expected validity interval of weak turbulence, which tells you that white caps would appear at much weaker winds that you would expect naively by just looking at your epsilon k. But of course, we cannot go into, by this approach, we cannot go into the domain where it's strong. No way, it's still perturbation theory. It's just as usual, I mean, like we used to, it's a renormalized perturbation theory. Your naive perturbation theory contains divergences. You resum it, you find out that it's actually singular perturbation theory. It goes in, which I probably won't go into details. But it's still perturbation theory. I mean, we are working with corrections so far. We don't speculate what happens when it's getting afford the unity, but we cannot so far go beyond it. So what it reminds us, all this K naught is L, right, is our kind of box size. But we actually get used to it in our incompressible turbulence. For example, our anomalous scaling in incompressible turbulence is actually tells us the following thing, that if you look at delta V in the power n, right, it's what is flux, I call it here P, times R in this is a dimensional estimate, and then you have this K over K naught or L over R in some power delta, and this delta tells you that if you are interested, for example, in the second moment, which is spectral density of turbulence, it goes to 0 when L goes to infinity if you keep the same flux. Physically, it's kind of, it's called intermittency, we get used to it. It tells you that to keep the same flux, you don't need all this turbulence, just more and more rare but strong fluctuations in a larger and larger box will provide you the same dissipation that you need, so your turbulence will actually level of spectral density of your turbulence goes to 0. So in a sense, what we find here, which is big surprise for me at least, something similar. It's not different. This anomalous exponent is not, you see, it's just scaling of interaction minus scaling of velocity, but not beta over 3 minus alpha. It's beta over 2 minus alpha. So this beta over 6 is our contribution to mankind in wave turbulence. But at least in a sense that the box size, the L dependence is natural in turbulence. So turbulence, even weak turbulence knows how many steps of the cascade you made. It knows how far away is this L is the pumping scale. On kind of more second thinking, I find natural, even though I did not foresee it. But the mostly interesting thing here is really not only the magnitude of L, but its sign. Because that's what we learned from field theory and the Nobel Prizes that they get at some point, that this L could be positive or it could be negative, right? And our first example was quantum electrodynamics, where this is negative, and what you had here is something which is positive, and when you increase, for example, that you see that it goes to 0, and there it's called zero charge situation or whatever. In our case, it would mean that as you go along the cascade and your L is negative, it suppresses. So multi-wave interaction suppress four-wave scattering. And if you look back into your equation for the flux, so if essentially this guys increases, that means that this would decrease. So you would see that your turbulence level would decrease, would increase. So this as a factor decreases, so your N would increase. So you would expect the strong turbulence would correspond to a more flat spectrum, not a more steep spectrum in this case, of Moscow 0. But on the other hand, if your L1, your effective coupling is positive, you have a quantum thermodynamic situation, namely that as you go along the cascade and L1 grows, you essentially enhance the interaction. And then at some point you hit the scale in which technically you get here pole, which we all learn, well, at least on a hand waving level, how people resolve it in quantum thermodynamics. They say, okay, this is a scale where the description in terms of our initial fields, quarks, gluons, is irrelevant, which we would tell our description of turbulence as a set of plane waves with almost random phases is irrelevant. What we'll have hadrons in quantum thermodynamics. What we have some bound states of waves. And this I find very exciting. And then we'll probably apparently will be our next step is for looking for it. But then again, remember, what is the white cap? What is the cusp on a C? It's a state of very many Fourier harmonic have their phases organized. This is a bound state. This is our hadron, right? Or solidon. Solidon is our bound state of plane waves. So now, what is the sign of this? I gave so many motivational talk. Now, what is the sign? I still find it breathtaking here that it's Lighthill criterion in a sense. So what it tells you, and this requires the analysis of this integral, and again, it's done only in the simplest cases. We still don't know what is the sign of effective coupling for, let's say, water waves on the surface. But for simple cases where we have this factorized or some factorized coupling, we find that it's a sign of nonlinearity times the sign of dispersion. If you remember, this is something which we learn that it's for a modulational instability of oscillator existence criterion in a nonlinear Schrödinger. So if you look at a monochromatic wave, which you can call condensate or quantum condensate, and you look at its perturbation, then the Bogoliubov spectrum is at lambda omega 2 prime times q squared plus positive term. So if your lambda omega 2 prime is negative, then at low q, you would have an instability. You would have imaginary omega, and that's a modulational Benjamin-Fair instability of waves on the water. But this is a criterion for a single wave. And here it's a very integral criterion. So in a sense, you need to take this parameter and weight it by turbulence spectrum, which is a power law, and integrate. And that, and depending, and generally lambda is a very sign changing function. So it's in every particular case, it will be a complicated and a very interesting study to find out the sign of this effective. But at least I find it very physically appealing that something even for a turbulent state, and there is no modulation stability for wide spectrum. If you consider a wide wave packet, it stabilizes modulation stability. There's no modulation stability. What we're making statistical statement. We're making that if lambda omega 2 prime would be negative, then effective coupling will be positive, and we would have a sufficiently large amplitude or a sufficiently long cascade, a state dominate a turbulence which is statistically dominated by bound states. So that's a statistical statement, not dynamical statement about instability of any given wave, but that it has this flavor of light hill. It's essentially a statement that the second, lambda is the second derivative of omega with respect to amplitude, and alpha is the second derivative of omega with respect to wave number. So this is probably the most physically interesting result of this research. Again, in a very simple, you see, this is something which is obtained for this trivial case of coupling, when we have a factorized coupling. So this is a very, very kind of a narrow class of system, and we still don't know what it is. But then now when we look at this picture and we say that indeed this cusp, which we see here, are the bound states, and then we may look back at our equation and say, if this equation contains such a solution, and of course such a solution was obtained, well, it's not a solution. The hypothesis of how the spectrum of cusp may look like is, we will find trivial to make, but it was a great scientist who actually made it, and it's called Phillips. And the argument was very simple. He says that if you have such thing like a cusp, then its Fourier image is 1 over k squared. So when you take square of it, it will give you 1 over k4. And it's independent on the amplitude. It does not matter how long the slope continues, right? Because essentially for the same amplitude, it would give you the same, it was called a universal spectrum. It's a pumping independent spectrum, which appears, of course, what is pumping dependent and at which car it's, at which wave number it starts. But then it's something which is universal, or it's sometimes called hypothesis of universal balance. And Goldreich and Schritthardt suggested this hypothesis of universal balance for Alfvén turbulence, for astrophysical applications, and Phillips suggested it here, and then Kadamtsev-Petrashvili suggested it for acoustic turbulence. So of course there are a lot of hypotheses. What we now show how to actually tell from the beginning which system would have this type of universal spectrum and which system would not. And the criterion is, like in quantum field theory, is a sign of effective coupling. So in this sense, I think that this is a certain progress here that we now can at least aspire, after complicated by straightforward calculation, to say which turbulence has a chance to have a universal equilibrium spectrum at sufficiently long cascade or large nonlinearities, and which turbulence is not, and will be determined by effective suppression of nonlinearity of four-wave scattering by multi-wave scattering. Okay, So this is more or less our so far qualitative answer. We did not compute it for surface waves. We may hypothesize that it will be like this, and it seems that all that alpha is less than unity there, etc. But lambda is very complicated. So now we are trying to compute this thing. Okay, and then at the moment that you think that it's so beautiful and so universal, we started to do second case, which is when this lambda is a sum, not a product. Here is for spin waves. It's just for, this is an expansion, first term of expansion of spin wave scattering because of exchange interaction, and we find situation different, which on a second thought is not surprising, because we are now trying to go beyond weak turbulence, that we get less universality. Thermal equilibrium does not depend on lambda at all. You can take any lambda. Thermal equilibrium is the same, at least in this weak nonlinearity limit. When you look at the Zakharov spectrum, it only depends on the scaling of lambda. It does not care about its dependencies of the wave vectors. Now we find out that the renormalization, is sensitive to what kind of functional form our lambda has. And we find out that this renormalized coupling now determined by 3 loop integrals, L0, L1, L2. And we find out that, for example, for spin waves, L0 always infrared divergence, L1 is converging, namely it's just epsilon k, it's a naive coupling, but L2 is always UV divergent. So in this case, we have enhancement. So in a sense, all this work is how non-locality enhances non-linearity in non-equilibrium. So you can kind of quantify it by how this ratio, your correction to Zakharov spectrum, is different from epsilon k. So it could be different because of infrared divergence, and here it is stronger than in the previous case. It's 2 beta over 3 instead of beta over 6. It's much stronger. It's practically always there. And but it's also a second type of corrections, which is something which behaves like this. It actually contains k maximum. And this nobody ever seen or predicted. So in a sense, we predict that for spin wave turbulence, the effective nonlinearity actually not only knows about how much behind in the cascade, but how much in front. What is actually the dissipation scale? I still don't have any intuitive picture for it. It's just a result of straightforward computations, and Vladimir did this. It's actually a very non-trivial computation. I mean, honestly, I must say that I tried to do it and failed, and he did it. And this is a really very beautiful solution, which I did not expect that it come out that beautiful. And L2 always diverge in the UV. So this is something which shows you that this correction to weak turbulence are sensitive to the functional form. Okay, and now to just put it into perspective and to more or less come to the end, I want to remind what was actually this modern kinetics and why it's something which inspired us. I was so ignorant that I did not know. They did not teach me when I was a student. I rediscovered it when we were working on electron kinetics with Levitov. So this is the following thing. This is a Boltzmann equation, which is again a quantum limit. It's quadratic in n, and it describes 2 particle collisions. And then if you want to do corrections to it, which will be just correction in the power of density. This is it's a dilute gas approximation. You assume that distances between collision is much larger than the radius of interaction. So what you need to account that the same particle could collide with the first particle. It's easy to do for Lorentz gas, where you assume that scattering is standing and not also moving, but it's actually irrelevant. It's just more ugly expressions. So you assume that one collide with the scatterer, goes somewhere, collides with some 2, and returns to the same scattering, right? So what good people at 70s, Green and Dorfman and Kuhn realized that you need to integrate now over R, over all the position of this second collision. And then if you consider contribution which is next order, rho cube, you need to integrate all positions of 2 and all positions of 3. Okay, of course, you have a small factor. So when to return from here to here, you need to be in the angle, this solid angle, which decays like r in the power d minus 1. So here is a competition between phase volume, which you get out of this integration, and the small angle scattering back. And so you just need to go, and in the Parrot's book, Surprises in Theoretical Physics, it's very beautifully explained. And actually this picture is, no, this is from our work with Levitov, but it's actually stolen from Parrot's, the same Parrot's who derived the kinetic equation for waves. And then you recognize that the contribution to Boltzmann equation behave like this. This 70s, that's modern kinetics. It's rho in the power n, and what stands here is r in the power n plus y minus d. So for any d, for sufficiently large n, it's infrared diverging. And this is, of course, now well known. It tells you that in 3 dimensions, you're pretty safe using Boltzmann equation. Your corrections are just rho squared. And when you sum all this, you get rho squared times log. But in 2D, you already have logarithmic correction in the first case. And in 1D, it just, in a sense, hydrodynamic does not exist. And it's now a very booming science when people study one-dimensional kinetics and find out how non-trivial it is and how similar it is from classical law. Okay, so in a sense, this is our analog of it, but they get these divergences in non-equilibrium, which is imposed in R space. Namely, you compute kinetic coefficients, viscosity, diffusivity. This is where you have these divergences. If you compute equation of state, everything converges because of detail balance. But also, Boltzmann equation incidentally contains Zakharov type solution, which also people from Zakharov school found. It's described pretty exotic physical situation, but they do exist. When you irradiate metals, but by a very hot radiation, you get a cascade in momentum space of electrons. And also in cosmic rays, which Landau studied at 30s, you also have cascades, which you can describe by a solution of Boltzmann equation, which has a power law in momentum space. And that's nobody yet analyzed. So this is again something which is kind of an open problem. So let me kind of wrap it up. So essentially, this is the question that we ask, and we discovered that it always infrared divergent. Namely, that your corrections to weak turbulence always depend on how large is the box size. So if you keep flux fixed and your current wave number fixed, and you take your pumping scale to infinity, you'll see that your effective level of nonlinearity increases. That's the main lesson. It's not of such a great practical importance. You know, there aren't that many very large intervals in astrophysics. Actually, there are, also. Oh, sorry. Oh my God. Current slide. Yeah. Somehow let me get back to where I was before I. Okay. And so in a sense, this is something which I may say that the small nonlinearity is getting, for this turbulent solution, is getting multiplied by a Reynolds number, which is essentially the ratio of scales. And so in some sense, kind of, there is no weak turbulence for sufficiently long cascade. And well, they already get their Nobel Prizes in direct metals, so and it's still a spectacular success, all this weak turbulence theory. But from a purely theoretical perspective, it's kind of sobering that really, and which I believe is a general lesson. So if I would give a general take-home lesson, as I would say that any perturbation theory in non-equilibrium is singular, and it's getting enhanced by some divergences. And opposite to what I thought 40 years ago, why I did not do this 40 years ago, is that I thought that these divergences are nuisance. And what I learned from field theory, and particularly from my co-author, is that they are a tool. That this divergence is actually a tool to learn an important physics. And that was, of course, field theory discovered in critical phenomena and everywhere. And that's what we now start to applying it here. So thank you very much for your attention.
Okay, thank you very much, everybody. Let's just, first of all, thank Grisha for a very interesting talk. I'm sure there must be a lot of questions. So I have several, but other people first.
Okay.
Anybody?
So may I ask a question?
Of course.
Yes, it should. Mhm.
Yeah, this is about what you said at the end, you refer to the kinetic Boltzmann equation. And I don't know if you know that, but this, stop there. This expansion in density, this is a topic that was very popular in the 1970s and 1970s, and I had made my PhD on that. It doesn't matter. But it happens that in 2-dimension, effectively you have a renormalization and you get a logarithm for 1/ρ in the expansion of the kinetic theory. But in 1 dimension, this changes, the renormalization changes not only the prefactor, but also you change the exponent, from, if I remember, from 1/2 to 1/3, which is a non-trivial renormalization effect. And
Exactly. Yeah. That's
that.
too much shame of me. I learned it only recently.
No
But
problem.
it's a direct analog. It's just
Yeah,
direct.
it looks very much the same, and in 1 dimension there is an interesting situation, and this is more or less explained in our review article with Pierre Rézibois in 1973, if I remember well.
Yes, that's your
Almost
exactly. Pomor is
50
about
years
paper.
ago. 50 years ago, So I'm glad to see that this topic is still alive.
Yeah, actually, as Grisha mentioned, I mean, there's been a big renaissance for the 1D case, and in particular, people like Herbert Spohn, but also a lot of young physicists are now actively involved in the 1D case.
Yeah, because it has non-trivial. What is interesting that for cascades for waves, space dimensionality does not matter. For in Boltzmann kinetics, is space dimensionality which determines, I mean, how ugly it's get. But in our case, because the parameter is actually, you see, Zakharov solution itself contains space dimensionality. So what only matters is the product of nk times k to the power d. So it only matters what is the scaling of lambda versus omega, and what is this asymptotics of lambda in large and small wave numbers. So, but conceptually, it's very similar. And of course, I was inspired by these things, by kinetics of 70s. Yeah, absolutely.
Yeah.
So, other questions? If not, I had a couple. So one question I had was, there's this old work of Erofeev and Malkin back in the 80s, in which they claimed to resum all the divergences and get a UV finite kinetic theory by using sort of the MSR approach. How, of course, they did mainly the 3-wave case, but how is your work related to theirs?
Well, I don't know, in a sense that we did not do 3-wave case. We need to now do 3-wave case in our way and then compare. Back then, because that was all in Novosibirsk, where I was still there, they were doing this work. I thought that that there was some computational errors there, but I would not claim it. This was kind of 30 plus years. So we'll check it. They definitely did not do it this way that we did it, and like by Simon the most divergent diagrams, and the expressions that they get, they look different.
Yes, absolutely. They sort of got a collision term that involved all powers of the nonlinearity. I mean, so there was, I mean,
from what I remember, that I look at that expression and I've seen divergences, and but then it unfortunately it was probably early 90s where we all started living everywhere, and so I tried to talk to Malkin, and then it was kind of but we'll get to it. Absolutely, yeah. Okay. We'll clear it out.
Yeah, so I mean, I agree that the spirit of what they did was not really like in the field theory RG. It was more like renormalization in the sense that Kriknen and other people use, which is kind of a resummation of replacing full, bare propagators by full propagators and things like that, and keeping nevertheless all the terms in the expansion. They definitely didn't resum most divergent diagrams, but
yeah. So what I try to at least what I remember, that I look at next terms and I've seen divergence, and I wrote to Malkin saying, no, they would cancel out. You don't see how they would cancel out. Okay, we'll check it. Three wave cases.
Yeah, that's particularly interesting for the case you mentioned about MHD, obviously. So there you have three-wave interactions of an interesting kind, and how you would go from the strong, from the turbulence to the Goldride Sridhar would be very interesting. So
it's unbelievable how stupid I was, because in 1996 I spent sabbatical at Princeton, and Goldride just did it, and so he came to me and started to explain. And I remember I was like, why would you assume that your linearity freezes at the order unity and stays order unity forever? I mean, what is the physical mechanism for it? And he said, well, I mean, what else could be? I said, well, then what else could be? Your effective interaction could grow, it could decay. Why is it frozen? And of course, Peter was right. I mean, in this case, and actually there are confirmation for it, but it took me again,
Yeah, I mean, I don't know about the general case, but at least
almost 30 years.
There are pretty clear physical reasons why you would expect that, because of sort of self-adjustment. I mean, if you go to too higher, then you start getting cancellations because of resonant interactions. So there's sort of a self-adjustment mechanism there. But in general, I mean, it's an interesting conjecture for other cases.
Yeah, in a sense, what I think is, for me, is most important here is I now have a criterion to say here it could be and here it could not be. Because otherwise, it's just, I mean, anybody can say, okay, and then spectrum would be such that minor linearity would stay for the unity. Why in this case it is such, and in this case it's not such? Now we have this beautiful criterion, at least for this kind of class of simple cases, where it tells you, well, look, this is a criterion, but how interaction and dispersion must be of the opposite sign. Naively you would say that it is something, you have bound state when lambda is negative, when wave attract each other. No, not when lambda is negative, when lambda omega 2 prime is negative. That's kind of, that's a physical. But of course, I mean, that's Goldreich paper is really great, and I did not understand it, and I feel really ashamed that I, argued with a great scientist and talking some nonsense to him. Well,
yeah. Anyways, they're smart guys, so I mean, it was
right.
That's an example where, I mean, even people like Bob Kriknen completely missed this, and they made it.
For this, I guess you really, look at back at 70s, I knew all the people who did. I mean, I knew Einstein, Weinstein, and Kriplovich who did this, confinement, renormalization, the sign, and of course I knew Landau people. So, and of course, and Polyakov could just, do it. Was very close to it in the early 90s. He actually get a student to do it, and the student was just a bad student, and Polyakov was doing other things. So that was something which could be easily done 40 years ago. When if did his work, just as natural would be to do this for another kinetic equation.
Okay, I have another question. Actually, this is related to your comment about Hasselmann. So, of course, Hasselmann was not cited for his work on kinetic theory in his Nobel Prize. He was actually cited for his work on climate modeling and study of variability and for predicting global warming. But there is a connection with Hasselmann's. Well, of course, the work on kinetic theory was maybe in the background too, right? But I mean, but that wasn't part of the citation. But the one interesting thing is that many of these closed equations have Langevin models. And, this is true for DIA, but also like in the work that I did with Xi, we found that the standard kinetic equation, you get self-consistent Langevin models, and they're completely equivalent to the standard kinetic equation. Have you investigated whether these new renormalized equations can be realized by Langevin models? So that would mean that I think maybe it's better. This is sort of an answer or part of an attempt to answer a question that Vladimir asked me at New York, which is what would be the advantage of an MSR approach as opposed to their perturbation scheme, which doesn't use the response function. And at least when you do it with MSR, you get two clear self-energies. One is like an effective damping, and the other one is an effective noise covariance.
Yeah, I'm on your side, absolutely. And that's what I also was telling Vladimir, that I think that this is particularly for analyzing infrared divergences, it's better to have two propagators. And it's more kind of, you have a clear picture. And in particularly, for example, for mass operator, for green function, you never have UV divergences, which is a much, much clearer case. But then again, it's probably could be doable anyway. I mean, but probably in some ways it would be more natural. There are many ways.
Yeah. So do you think that there is a Langevin model realization? So in that sense, you would
That's I don't know.
That would be
I
a
don't
direct connection with Hasselmann's work in the sense that now for this set of wave systems, you would have a way of representing sort of the turbulent intrinsic wave noise that's produced by all these divergences. Yeah, I think that we'll probably need to just sit down and try to write it. I don't know. I never tried. Incidentally, a kinetic equation is called Hasselmann equation in oceanology. So it's really kind of a part of his models, which he applied was directly kinetic equation, which they called Hasselmann equation, even though it was like 40 years after Peierls, which I always made me mad. But he did great things, of course, with all this practical things. Well, of course, he was upset himself that he didn't know it, right? That, I mean, he rediscovered it and he was very embarrassed after he found that it had been done so much earlier by Peierls and said, oh, you know, this shows the lack of communication between different fields. You know, we should have all known this. And, but, okay, so let's see, I had one other question, which is the sort of the relationship with QCD. So of course, in QCD, when you do the perturbation theory, you do get infrared divergences that tell you that the perturbation theory is breaking down, but you can't really go too far in pushing the perturbation theory to talk about the infrared regime, right? You then really have to bring in new non-perturbative ideas, you know, so Wilson loops and things like that. The same here, absolutely. Yeah. We cannot go beyond this, absolutely. Yeah, we can just, but we get, if what we can get, we get a prediction that something happens, that there is a phase transition at some scale. But the nature of it, we cannot get by this approach. You need more creative things, which could be doable. But when you look at real lambda for gravity, for surface water waves, it's so damn complicated. I mean, I already spent a few weeks doing different. I mean, it changes sign on complicated surfaces. So it's not easy to do it, but there are some creative ideas here. But definitely not the straightforward approach. Cannot get us beyond the like in QCD, of course. Yes. Okay. Any other questions?
Yeah. I've got a dumb question. So Grisha, so if I understood correctly, correct me if I'm wrong, but this still uses fluctuation dissipation theorem, right? No. If it's actually what is Vladimir now computing is which again it's a very interesting thing. For example, you have this forcing and you have your dissipation at the very beginning. I have this F at gamma, but they aren't in a fluctuation dissipation relation because my NKs, which is their ratio, is not equipartition. So if you look at different time correlation function of two amplitudes and differentiate it, it's not equal to the green function. There are some differences. Okay. Okay, good. Because your NK is not equipartition. Yeah. So then great. That's what good. So that was so then but it should also then since then we learned also many things about non-equilibrium fluctuation dissipation theorems like Harada-Sasser result and things like this. How does that result relate to these known results like Harada-Sasser and so on?
I don't know. That's very interesting. That's exactly what we were talking right now, that we actually need to look at this difference and present it in this indeed a general form in which people get the general fluctuation relations. I always wanted to have it in turbulence, and here at last we have a perturbative case where it's computable. So it's but at the moment the answer is I don't know.
Right, but you don't necessarily need to be able to approach it just from the point of view of perturbation theory, particularly if perturbation theory is so singular like it is here. I mean, the singularity of perturbation theory may obscure what is actually a very simple physical relation.
Right. But in a sense, it's really, the true approach is always entropic, right? So if you really know, what is your entropy, then it's usually you get a right identity. You get Kierzyński for free, you get Katanasasov kind of almost for free. Here, I don't know. This is something work which is cut for us right here.
Okay, let me ask you a question then about the analog of Moscow zero that you mentioned in the middle. So this bound state. This content here, I was kind of interested in that. Is that if you have if such a thing is physical, which I have no idea whether it is, but I mean, is there any possible connection between the existence of such a feature in the spectrum and rogue waves?
I don't know, because for me, rogue waves is a statistical statement. It just says it's some kind of, it's really kind of fat tails, because in a sense, the rogue waves, it's not necessarily such a bound state. It could be actually quasi-periodic, because it's just a statement that some very strong fluctuation happened with non-zero possibility, but it could be related. In particular,
it could also be a repeated scattering, like if you were doing this in many body theory, with electrons, you would go to, say, the strong scattering limit where you have unitary scattering, and then you can get different effects that come from these multiple resonances. So is there anything
that I would dream to do for water waves? I would want to just guess. And technically, I mean, my idea is as following: that of course this lambda is damn complicated, but if I'm really looking for such like a rogue wave, or it's just a cusp, it's locally one-dimensional. It's just a front. Which means I need to analyze it for lambda 1, 2, 3, 4, all 1, 2, 3, 4 almost parallel. That simplifies it hugely.
Yeah, exactly. When you look at extreme events, lots of things simplify and correlations go to 1 and things like this. So it's
so my hope here
is much easier than just looking at the regular weak fluctuation limits. And sometimes a strong fluctuation case is much more physically interesting anyway and easier.
I just finished writing a proposal where I say exactly that. This seems hopeless, and yet, if I assume local one-dimensionality, maybe it's manageable. Even that you can really try to guess what is the true solution of this integral equation, and then the nature of renormalization over there. But then again, has not been done. This just look, we just started. I mean,
thank you.
Okay, and any other questions or comments? Okay, I guess if not, then let's thank Grisha again for giving a very stimulating talk, and we'll look forward to hearing about further developments.
Yeah, thanks a lot.
Okay.
Thanks, sir. Nice to meet you, Vladimir.
Nice to meet you.
Okay. Okay, bye-bye.